Yeah, so I thought what I would do today is maybe talk a little bit about some of the peripheral systems that need to be upgraded and managed in order to successfully integrate automation, in particular autonomous vehicles, into the transportation system. And so what I'll do is I'll focus on one aspect of the larger system, which is curbside management. I hope to kind of give a sense of, what has been done in the past, a little bit about what's currently being done, and then a little bit of a vision for the future, where there I'll talk a little bit more about the potential opportunities for autonomous vehicles and changing the landscape based on the introduction of autonomous vehicles. Okay, so just to sort of set the tone or give a little bit of motivation, although perhaps most of us don't need this. So the transportation system over the last, say, 20 years has really seen a pretty significant change in terms of the types of modes of transit that people use and the types of physical infrastructure, cyber physical infrastructure, Internet of Things infrastructure that's been integrated into these systems to help, overall efficiency, amongst other things. And one of the aspects that we're seeing a significant change in is the management of curbside space, as well as how we allocate the travelway itself to different purposes. So just to give some, this is not really statistics, but just some, kind of cartoon about what the changing landscape looks like from 2010 to 2020. I took this graphic from the SF-MTA 2020 Curbside Management Strategy Report. And basically it's showing that, in 2010, we mostly had these personal modes of transit, and then, publicly or transportation authority managed modes of transit. Whereas in 2020, we now have all of these additional private companies which have introduced various shared modes. And some of these are also, of course, managed by cities. And some of these shared modes include things like bike share, scooter, and other micro vehicle share. There's also now these private company transit commuter buses. So like, for example, with Google and other companies that hire their own shuttles to pick people up. And then, of course, we have rideshare, and concierge network service companies. So things like Amazon Flex or Uber Eats or whatever. And all of these guys are in need of curbside space, either for storage of the vehicles or drop-off pickup points. And so that's introducing much more competition for how we use curbside space. Okay, so then in addition to this, because of these new modes, amongst, sort of a push to have space for things like parks so that people can exercise, or space for things like commerce, say food trucks, there's a number of new management objectives. Just to kind of go through them. So the first is really understanding how we can replan and repurpose space so that we can integrate things like community space, as well as green space. One of the interesting things, I think, from a learning and control perspective is the introduction of these flex zones. So basically, this is a time of day zoning change. So you say, for example, in the morning, you might have pickup and drop off of, passengers, perhaps, to facilitate people going to work. In the afternoon, you give this space to commercial load zones so that they can drop off packages and things like this, or goods to companies. And then in the evening, maybe you have public parking to service business in the area, like restaurants and things like that, or even residents. And so understanding exactly, how to allocate this space, what the schedule should be, is quite an interesting problem. In addition to this, we're seeing new markets and automated pricing. So for example, with these flex zones, you might now charge commercial vehicles for using them for certain amounts of time. And so understanding how to adjust these prices appropriately is also a challenging problem. And sort of the last thing would be this automated enforcement and compliance. So I don't know if this is common in other cities, but what's happening in Seattle, after all of the issues with police and other things this year, some of the components that were previously under the purview of the police are now like falling into other departments within the city. And one of those is parking enforcement, for example. So that's now being integrated into SDOT as opposed to being part of the police. And so one of the things they're looking to do is to be able to integrate more automation into this compliance process, and then also be able to leverage this data to help reinforce their understanding of curbside usage. So there's these sort of interesting array of different management objectives that come along with this changing landscape. That's sort of the summary. But there's a number of challenges that go along with this. And so I'll start with some of the human side of things, and then talk a little bit about the interface between sociological and technical components. So first of all, humans are not necessarily completely rational. And so really this challenge introduces some technical issues with respect to optimization and control. So most behavioral models, for example, are not smooth. There's various timescales in the decision making. So this makes designing, for example, incentives or other mechanisms to shape behavior non-trivial. Moreover, there's issues with data quality. Often it's quite sparse or inherently biased. So if we go back to that example where I was saying now we can use, say, enforcement data to understand curbside usage, well, if you just think about who is collecting that data, let's say it's a parking enforcement officer, and they get to decide maybe their general path for observing, what the parking behavior is. And maybe they decide always to go by their same favorite coffee shop every morning, and then the data they collect is always going to have, a sample from that particular area. So that's a sort of innocuous example of how bias can be introduced into the data set, but you can imagine much more nefarious ways in which bias can be introduced, such as only collecting data in certain neighborhoods. Beyond this, we have now a number of different automated decision-making processes. And so this includes algorithms and autonomous agents interacting with humans. And so this leads to non-stationary environments. And then, of course, there's these new markets, which lead to kind of complex private-public interactions and resource consumption that perhaps exacerbates this issue of the tragedy of commons, overuse of public goods in particular. Okay, so then, sort of at the interface of the social and technical spaces, some of the challenges include the fact that we have legacy equipment, and moreover, at present, at least, a lot of the equipment is rapidly evolving, and they really haven't settled on a technology. So as an example of this, and I'll talk more about the parking as a specific case study in a minute, but in Seattle, only a few years ago, they decided to transition away from classic coin-based meters to smart meters. And now there's sort of a secondary push to kind of go away from any kind of parking meter along the block face, digital or otherwise, to using only pay-by-phone type apps. Of course, you can't get rid of all of the meters, because that's, not possible if everybody doesn't have, if all your user base doesn't have the technology. However, there is a push to reduce the number of these digital meters that exist, the physical meters that exist. So yeah, there's this still sort of like unsettled technology changes that are occurring. In addition, we see that cities have very tight budgets. I think this is very true now in particular. and they're quite policy constrained. So this gives rise to issues on the technical side from the perspective of, whether or not you have in-house expertise or the money to hire those people to manage things like large data sets or to understand the data that you're collecting from new technologies that you integrate into the system. And as I already sort of mentioned, you can't just assume that you can replace everything with one type of new technology that's going to make everything better, like, say, paying for parking using a phone, if not everybody has access to that kind of technology. So you have to always sort of deal with this, broad range of types of technologies that the different user pool has access to. Okay, so as I mentioned, I'll kind of now maybe focus a little bit on specifically the one aspect or one aspect of curbside usage, which is parking, so on-street parking, where, in my group, we've done a little bit of work. And so I at least have an opinion about it. And what my goal will be to do is, as already mentioned, sort of cover what's been done in the past, what's happening in the present, and then spend a small amount of time towards the end of the talk talking a little bit about, what we can do in the future. Okay, so just to motivate why we should even care about the on-street parking problem. So there is sort of a push to kind of reduce the curb space allocation for on-street parking in many cities. There was actually a nice New York Times article with like a really nice like virtual, I don't know what they call it, virtual storytelling or something like this. It had some really nice graphics, and basically they're advocating, getting rid of driving, like personal vehicle driving in Manhattan, and reallocating curb space usage to all kinds of things, including parks and social service centers and so on. And so even though there's the push for that, we still have in most places a significant chunk of the curbside space allocated to on-street parking. And so at present, there's still a need to deal with this problem. So one of the challenges is that people spend a significant amount of time in the search for parking. And this causes unwanted congestion, as well as like reduction in business district vitality, and can be a problem for people who live there if they can't find a place to park. And so this little clip, I'd be curious, how this has actually changed over the last year. But these statistics were at least relevant, as of 2019. They were taken in 2017, but our behavior probably didn't change that significantly. And it basically just shows in some of our major cities here in the U.S., how much time people are spending searching for parking. And some of these numbers are pretty exorbitant. If you look at the annual search in hours per driver per year, it's I don't know, that seems a little bit wasteful. So the way that cities manage these issues, and some of this has been, there are cities who are doing an exceptionally good job, arguably, at going beyond these classical methods. For example, LA has LA Express Park. And so this perspective that I'm talking about is more from the point of view of what happens in Seattle and perhaps other cities which haven't adopted some of the newer technologies and dynamic pricing mechanisms. And so sort of, the historical way prices are set is to really balance multiple objectives. So reducing congestion, increasing business district vitality, and making sure that residents have access. And then revenue is a secondary, typically a secondary consideration. And so the way that prices are set is that you establish this sort of target occupancy range for each block face, and usually it's fixed for every block face, independent of what is actually going on in those neighborhoods. And the rule of thumb is that you should be somewhere between the 60 and 80%. And then these, in order to determine the prices, annual studies are conducted to get manual counts of the parked cars. So this is typically occurs over, like you basically get a 1 day sample for each block. And then this data with past manual counts is used to determine whether or not there are going to be changes in the, the pricing schedule, which tends to be like time of day fixed pricing. So as I've already noted, there's, the introduction of these smart meters and pay by phone technologies, which allow us to collect, a richer data set in at a faster pace than previously. So typically the data from these smart meters and pay by phone here in Seattle, you can get the new data like at the evening, after the evening of any particular day. So there's an opportunity to build better models based on this transaction data along with manual counts. Okay, so then with this sort of these observations, the objective that I'll talk about, and I'll talk about two sort of lines of work that at a very high level that we've been doing here within, addressing this larger objective. And the goal is, like, at present, given sort of the policy and technology constraints that we have, how can we develop algorithms that adjust parking policies? And in particular, I'll focus on this issue of how to design both pricing and information mechanisms to change behavior, but ultimately we would like to be able to think about other uses of the curbside space. And so the first thing I'll talk about is methods for adaptive inference. So we want to move beyond these policy changes or pricing changes that are based on single day per year studies and go to a more data-informed model-based decision-making where we use adaptive data collection. So specifically, we want to say, okay, well, if I have a reasonable model, how do I then go and choose areas to conduct targeted studies that are going to give me data that's most informative for improving that model? And then once I have this kind of model, I can use it for things like inferring, what curbside usage is going to look like and predicting perhaps future curbside usage, in particular for parking. Okay, so
hey, Lily.
Yeah.
Rujna has a question about some of the motivations. Maybe we can quickly answer that question. So Rujna, I just asked you to unmute if you want to ask your question yourself.
Yeah, I'm sure you have noticed that because of the coronavirus, the many companies are finding out that it's not necessary to rent all the office spaces because people can equally profitably work from home. Now, will that, I'm sure it will have an impact on parking demands and driving. So have you thought about that?
Yeah, of course. That's a great question. And so we really don't have the data yet. And so in Seattle, for example, they closed all the parking and then reopened it in July. Well, not closed it, but, made it free. So they basically weren't managing it. And then reopened it as paid parking at like 50 cents an hour or something, some small price in July. And so we're starting to get more data now on what the parking usage is, and hence we'll be able to see what the changes are. But from the preliminary data, it does look like it's significantly changed. But that's a fantastic thing, actually, because if it means less people are using the space, then we can, reduce the number of spots for on-street parking and start thinking about these flex zones, which are more for like passenger drop off and package drop off.
But in your calculations for what is optimal or semi-optimal, you may have to add the dynamic component that things will be in flux. Some people say that this situation will last for another 2 years. Some others say it may last 5 years. Nobody knows.
Yeah, you're absolutely right. Yeah, that's and perhaps at the end when I talk about sort of the future, near future,
yes.
I can give a little bit of a sense of what we're thinking about in that space. Okay, thanks for the question. Yeah, so first, so just kind of we're going to think about how to do adaptive inference. And what I'll first do is talk about how to just use the data that we currently have to get sort of a static model, and then how to improve these kinds of static models by doing adaptive data collection. And so one of the reasons that understanding parking occupancy is challenging is that there's a variety of different aspects that actually motivate how people decide where to park. It's not just things like price, even though price is really one of the primary control levers that cities have. So first, several studies have confirmed this, but for example, the SF Park one that was done a while back, and then also all of the data that is collected through LA Express Park, and specifically their study that was done with the original funding, has confirmed this, that basically price elasticities can significantly vary spatially across a city as well as temporally. So that makes setting prices challenging, because you have to figure out sort of what is the right set of contiguous, especially if it's zone based. You have to figure out what is the right set of contiguous blocks to set and time period to sort of set prices appropriately, or set prices to achieve your objective. The other thing is that it's not price really that is the primary driver of parking, but rather rather location. So in one study in LA, it suggested that 50% of people parked within 1 block of their intended location. The other thing that's important is information or lack thereof. So many surveys have been conducted which have indicated that most people who are parking don't even know what price they paid. And so this little diagram on the right is basically from LA Express Park study, which basically it was asking through 2 different survey mechanisms whether people were aware of pricing changes, whether they were aware there's time of day pricing, and whether they were aware of a mobile app that existed to tell you about this information and actually, or tell you about these changes. And the statistics are pretty telling that most people were not aware. Okay. So let's focus on this zone-based pricing in Seattle. Oh, sorry, I meant to take that slide out. Okay. Yeah. So the goal will be to come up with a method that works within the policy constraints and the set of data that we currently have, so that we can do something impactful at present. And just to remind you, the prices here are typically set to hit a target occupancy. Right now, there's these predefined zones, which are done based on just some heuristics, some neighborhood heuristics. So for example, in the plot on the left, you're looking at Belltown, and it's just sort of, I wouldn't say arbitrarily defined into a north and south zone, but there's this one main street that's used as like a dividing line for the north and the south region. And it's not clear why that was picked. It certainly wasn't picked based on any data-informed reasoning. And at present, again, prices are only revised yearly. So we have to sort of stay within that policy constraint. Observable data includes this parking transactions, basically, which isn't necessarily reflective of actual occupancy, but does give a good picture on aggregate of what the use is like. it's less good for like individual blocks. We also know sort of these block locations and neighborhood boundaries. And so we want to take the data that we have and come up with first a spatial temporal analysis to create these like data informed zones that are more reflective of how how people actually use the curbside space for parking. And then once we do that, then of course, within these zones, quasi-static prices can be set in order to kind of have macro level control. And then ultimately, we'd like to be able to target information incentives, say at the individual block level, which I'll talk about time permitting in a couple slides, in order to have more refined control of the parking behavior. Okay, so we did probably the most simple thing that one could do, because why not start with a simple model if it turns out to be informative? And in this case, it did. So we just did a Gaussian mixture model for so Seattle, like many cities, is broken into larger zones, which then have like subzones. So for each of the larger zones, we developed a Gaussian mixture model to kind of basically group together blocks with similar occupancy characteristics in order to sort of figure out what the best partitioning of the blocks is into zones that again are more reflective of usage. And so I'll just show a couple outcomes of this in terms of plots or via plots. And we basically used paid transactions from the 2 years, 2016 and 2017 for this. Okay, so based on this work, if we just focus on Belltown, the reason we picked Belltown is that it's a highly mixed-use neighborhood. So, and it's the most dense in terms of where parking, like which blocks have parking, on-street parking. So as you can see from this picture, almost every block has on-street parking. So all the colored ones do in the right picture. The right picture is also the current division of Belltown, as mentioned before. And then the left picture is a representative division of the blocks into new zones based on this Gaussian mixture model. And so the red dots that you see, those are like the center of these clusters. And the colored dots sort of indicate which cluster a particular block belongs to. And then the concentric ellipses essentially tell you about the spatial variation. So there's a couple things to observe about this. So the first thing I'll say is that weekdays are all fairly consistent. So meaning that the weekday behavior actually has almost exactly the same sort of trends from like Monday to Friday. They're basically interchangeable. And then Saturday has a totally different behavior, which is probably to be expected. So I don't have any plots to show you that, but you can take my word for it. So the other thing to sort of notice about this is that without us putting this information in, these groupings are pretty interpretable. So in this area of Belltown, the magenta colored blocks, those are basically the area that has a really high density of restaurants. And it also sort of abuts basically the financial district and shopping district that's downtown. The dark blue dots, that's where we have like a bunch of museums and other tourist attractions. The cyan color dots, those are residential, primarily residential area. And then the green area is like another sort of tourist attraction and the waterfront. So this is where all the cruise ships come in and unload and things like that. And there's the sculpture garden up to the just slightly north of that area. So like without even, inputting this information, sort of it's suggesting that the parking use is reflective of like what the neighborhood characteristics or what the location characteristics look like. So as I mentioned, the weekdays are basically the same. The other interesting thing is it turns out that, meaning we get the same sort of mixture model for weekdays. It's consistent. It's also consistent within 2 time periods of weekdays, so between 8 a.m. and 3 p.m. and then 3 p.m. and 8 p.m. You get slightly different models, but they're consistent within those time periods. And so that suggests, for example, that you can break the blocks up into these different suggested zones, and then within these 2 time periods, perhaps have different pricing. So another natural question is whether or not price is really the reason for the observed mixture components. And so what we did is we looked at this 2016, which had a price of $1.50 an hour in the north zone, and 2017, which it was reduced to $1 an hour. The south zone was kept at $1.50 an hour. And so the zoning or the Gaussian mixture models look pretty similar. And then also what's interesting is actually just looking at the change in occupancy. I didn't mention, but the price change was only between 8 and 11 a.m. in the morning. So if you look at this north, the change in occupancy in the north zone, so each of the vertical bars is a time during the day. So paid parking only occurs, it did during these years between 8 and 6, I think. It's now been expanded to much later. But you see positive changes, actually more increase in occupancy during the time in which the price was reduced, which is interesting. So that means that more people are parking there, even though it's yeah, is that right? Oh, yeah. So you see this. Yeah, sorry. Actually, that doesn't make sense. Sorry. So you see basically a very small change in the north zone, even though it was reduced price. And you see a significant change in the south zone, even though it remained at the same price. So basically the point is that it doesn't appear that this small changes in price are actually driving where the centers of demand, so where people are choosing to park. Okay, so just to wrap this up, I only have like 8 minutes left, I guess, so try to finish the last bit of the talk. So the nice thing about these static models is that they work with the data that we currently have and within the sort of policy constraints. And so they give us some suggestions about how to do better zoning or data-informed zoning, which correlates with things like land use. And the downside is that they're only using paid transactions. So they really just give us a more system level view of behavior, and they have limited predictive power, if any, for individual block behavior. So that means that they're not going to be useful for things like adaptive pricing. So really what we want to do is figure out how to refine models like these by figuring out exactly where to conduct studies with the limited resources we have to get ground truth data. And so we've developed some techniques for doing this adaptive sampling. I won't talk about this too much, but there's really 2 ways you can do this. One is through these targeted studies, and then the other is through, enabling this newly acquired enforcement component of the parking management system to help you collect data on a daily basis from particular blocks of interest. And so the thing that I guess is important is really that context is important. And so what I mean by this is that, as noted, Friday or weekday versus Saturday, there's very different behaviors. So these are just contour plots showing what the occupancy level is on average in the particular hour shown. And the other thing is that other environment contexts like weather is also important. So there's drastic difference in how people are using parking when it's rainy versus not, which is a big consideration here when it rains half the year. We've entered the dark period, as I like to call it. So hopefully the time change will help with that. But yeah, so environmental context is important. And so I don't have time to get into what we've done, but basically we've developed some pure exploration strategies for contextual bandit problems that allow us to figure out what are the most informative places to sample. And the next steps are working with SDOT to implement this, and they're actually, because of COVID, and budget constraints and things like that, they're more amenable to allowing model-based methods for setting prices and things like that. So actually that's been a positive change from my research perspective. And so the company they work with that does all the testing, we're collaborating with them now to figure out how to implement these algorithms that we've developed for adaptive sampling. Okay, so I'll quickly go through this second thing. So as I mentioned, at the macro level, you can set these quasi-static prices, perhaps to change behavior, and you're still doing it within the policy constraints that you have. On the other hand, maybe you want to refine the reuse of the curbside space by trying to influence individual behavior or individual block behavior. And so what we've been thinking about is how to design information-based mechanisms to do this. So in Seattle, the app that is used is Pay by Phone. There's, for example, in LA, there's like 10 apps that you can use, but the premise is basically the same. You want to be able to offer information to people in various different forms. So you want to decide which type of information is going to be the most effective at changing different users' behavior. In addition, you might also offer incentives attached to locations, which some of these apps are now doing. Okay, so the challenge is that people actually make decisions by comparing to reference points. So we want to sort of shape these reference points. However, they're not static. They change in time based on whatever signals we're giving them, and then also potentially some environmental things that we don't have control over. And we do not have observability of individual behavior, but rather some aggregate behavior. So basically how we're thinking about this problem is, sort of in this feedback loop. So we want to shape the information that people get. This is going to affect, how they're, what they're comparing to, their reference point in making their decision about where to park. Perhaps there's some other exogenous inputs like incentives, and then they make a decision. So we sort of have this feedback loop. And so, as I mentioned, the challenge is that we only observe, behavior at the block level based on, say, things like paid transactions. So what we do is, instead of attaching reference points to individuals, we attach reference points to locations, and then think about how to target incentives or information at those locations in order to shape the behavior that we observe. So there's a challenge that, these blocks are interconnected. So there's sort of a correlation between the block usage. The reference points change in time as a function of the incentives offered. And we have a budget on incentives or information. We have a budget on the amount of these signals that we can give out. So we then model this as a combinatorial multi-arm bandit instance, where at each round, we basically solve a matching subject to some budget constraints, or we match a set of incentives to a set of locations. So I won't go through the details of, this was all high level anyway, but basically the idea here is that, we only observe some aggregate information, and we want to solve a matching problem at each instance. There's some correlation between the decision problems because the reference points itself evolves over time. And so what we do is we essentially modify existing upper confidence bound approaches to account for this evolution of the environment, this non-stationarity that occurs due to the evolving reference point. And then if we modify these existing algorithms, then we can basically try to obtain regret bounds, which means we compare the best thing you could have done to like what we actually did. So Essentially, the takeaway is that we combine upper confidence bound methods with a greedy matching algorithm that allows us to bound suboptimalities that cascade as a result of bad matches. And do this by basically fixing the reward that we're going to, like the matching, for an amount of time. So this would say, like, we would offer a set of incentives to locations for a full day, and then observe like sort of the time average behavior of whatever observation variable we have. So for example, occupancy and how well it's matching the target occupancy level. And then based on that information, we would then make another decision about how to solve a matching in the next time instance. And so by allowing the matching to be fixed, essentially this lets the underlying Markov process mix enough that we can still obtain good regret bounds. And so the regret bounds basically are still the same as they would be if you were doing, as they are with classic UCB. So they're logarithmic in the number of epochs, so the number of fixed times, which is a sort of technical point. Okay, so then the next steps, I know I'm running out short on time, so the next steps would be then to now take this and apply it in the real world. So there's a number of technical challenges associated with that, but that's what we're working towards. We were trying to do this, earlier in the year, but then with the whole COVID situation, everything basically got put on hold. So we'll see where we are, what makes sense when things start ramping up again. Okay, so this is just to sort of summarize. Basically, we talked a bit about specific type of curbside usage, and how we can use existing technologies to improve the efficiency of the use of that curb space. So just to remind you, we said that in the past things are set heuristically based on one-day counts. There really wasn't full integration of new technology-based solutions. And now we have methods to go beyond this and to have model-based methods of being able to set prices that are based on the data that we collect, and we can adaptively collect that data in order to improve our model. And now we have this set of robust micro-level influence mechanisms that we can implement to sort of refine the curbside usage. So then let's see, in the last slide, what the future perspective sort of is. And I'll just comment briefly on this. So basically, sort of the vision, I guess, for these curb spaces is to actually reduce any of this on-street parking and allow the space to be repurposed for a variety of different things, including, having, I guess, I've seen this in several of these city reports, what they call activation zones. And I guess that's like, space for exercise. You want to have more space for commercial drop-offs. So that includes things like Amazon Flex drivers, so smaller vehicles that are doing deliveries and things like that. You want to have limited storage space for parking. You want to be able to expand greenways to allow, more positive uses of curbside space that are, help build community and things like that. And then, of course, as we move into the future of maybe quite a bit down the road of the transportation system, we need to be able to integrate whatever designs we do now. We need them to be flexible enough to be able to integrate, new technologies like, for example, mechanisms to adaptively change zones from, say, like a commercial loading zone to a passenger loading zone to a storage space, or to one of these activation zones. And so whatever, it makes sense, I think, at present to think about this in the design now so that we're able to integrate these new technologies without, causing a huge amount of, budget or expenses that, are unwarranted. Right. And so, yeah, I guess I'll just finish with that. So if there's any questions, I'd be happy to answer them.